Thank you everybody for coming. I think before we kick off, we need to give a big thanks to both the Faculty of Arts and Science, the Visiting Scholar Fund, which is graciously inviting Sheila here for 2 days of a packed schedule of events and one-on-one meetings and a number of things, but also Ingenuity Labs for hosting us here in the space that we have. So a round of applause for Ingenuity Labs and all the way to FAS so they can hear us too. So I want to keep the intro relatively short to sort of maximize the time that you have. If you look at any email you might receive from Sheila, every one of the taglines on her signature is something you could aspire to in your career, right? One after the other: professor in the Department of Computer Science at U of T, Canadian CFAR AI chair, associate director of the research lead of the Schwartz Reisman Institute for Technology and Society, faculty affiliate with the Vector Institute. All of these things are kind of like your goalposts or what you're shooting for in terms of an academic career, and very, very impressive. AI 2050 Senior Fellow of the ACM and AAAI, a number of paper awards and so on. Relevant to those that will be joining us tomorrow for the ethics seminar, founder and lead of the award-winning Embedded Ethics Education Initiative, the E3I. But one aspect that you won't see in her sort of tagline is sort of the compassion and the ability to lift up the students in her career. So I do want to mention one thing that I think makes Sheila sort of shine as a researcher and why it's so great to have her here. Some of my students know the history of it, but I nearly missed my entire academic path by not understanding how the process worked. I think my interview went okay. Coming out of undergrad, it was with Sheila I did the interview, but it wasn't until I think mid-August that I reached out and said, I haven't received any information. Do I pick courses? What's going on? And she said, you are not registered for U of T. And so I had misunderstood the entire process, and through a lot of backroom finagling, just as she was entering parental leave, she managed to sneak me in the back door. So depending on your perspective, you either have Sheila to thank or to blame for me being here at Queen's at a number of points. So thank you very much, Sheila, for coming in. And once again, everybody please join me in thanking Sheila for the presentation.
Thank you, Christian, and thank you very much to Queen's University from me as well. It's my tremendous pleasure to be here, and I'm really looking forward to interacting with at least some or many of you during the 2 days that I'm here. I'm trying to discreetly stick this on my back. Just a second, sorry. Oop, maybe I'll put it here. Okay, very good. Yeah, so thank you. And yes, I've achieved many things, but it's been done with my students, and they, including Christian, Professor Muse, who's contributed to, and many of my other students who've contributed to the accomplishments that we have collectively received. So today I want to talk about how formal languages can help AI agents learn, plan, and remember. And in keeping with what I said, a lot of the work that I'm going to talk about today was the PhD work of Rodrigo Toro-Carta. He's now a faculty member at the Catholic University in Santiago, Chile, and it was done in collaboration with Torren Clausen, who's now a postdoc, soon to be research associate at University of Toronto, Rick Valenzano, who's Torren was a student at the time, Rick was a postdoc at the time, and now is at TMU. At the University in Toronto, as well as some of these other students who've done related work that I'll be talking about today. So what I want to talk about is sequential decision making, and I just stuck a couple of slides as sort of a preamble to my talk, just to sort of situate us, because I know this is a fairly a diverse audience that sort of comes to the problem of sequential decision making from many different pathways. So a sequential decision making problem is a problem where you're making decisions over time about how to act in the world. So we can think about, we have lots of robots here, a robot making a sequence of decisions in order to pick up something or control something or to navigate in a particular environment, a conversational agent that's making a sequence of decisions in order to have a conversation or to convey some information to another agent. There are all sorts of different applications for sequential decision making. And as a consequence, many of you probably come to this using a different set of techniques. But the essential building blocks are that we have some sort of model of environment behavior. We create some representation of state, possibly from a partially or fully observable environment. We have an agent, a robot or a bot that has some actions that can perform. Those actions have effects in the world. And then we have the agent has some sort of an objective. And we formalize those things in different ways depending upon where we come from and what we know. So if you're in control systems, maybe you write a transition function, various other things. If you're in AI proper, perhaps you write an MDP, transition model, and a Markov decision process, model it as a Markov decision process with a set of utility functions. If you're a symbolic planning person, maybe you write P2DL. And if you're a formal methods person who does program synthesis, perhaps you write a formal specification and hope to do correct by construction synthesis from that formal specification. The problem we're interested that I want to talk about today is where some of these things are unknown. We don't know the environment behavior, and we don't actually know the effects of action. So I know I have I know I can press the red button, the green button, and the blue button, but I don't know what happens when I do that. Or I know I've got an action called foobar, but I don't know what its consequences are in the world. And so I'm trying to learn how to act in the world based upon that limited knowledge. And what I want to do is I want to synthesize a policy, which is a mapping from state to actions or an action distribution, so that in any state that I'm in, that policy tells me what to do. That's going to be our solution form that we're interested in. And what I want to talk, and we're going to do this in the context of reinforcement learning, which is a particular paradigm for doing learning, where the agent takes an action in the environment returns the state and some sort of a reward for that state. And through a series of sort of trial and error exploration, what the agent wants to do is wants to learn a policy, a mapping from state to action or action distribution that maximizes its expected cumulative reward. So that's the problem we're going to be looking at. And in the context of that, and again, I guess I should mention here that sometimes we have perception here. We're not necessarily just dealing with a state that's well represented. We may have different modalities of perception. We could have vision or language or LiDAR or auditory signals that we're using in order to model that state. With that in mind, I wanted to start, and I wanted I'm just going to read this because I want to talk about language, getting back to the title of this talk. So humans have evolved language over tens of thousands of years to provide useful abstractions for understanding and interacting with each other and with the physical world. The claim advanced by some is that language influences what we think, what we perceive, how we focus our attention, and what we remember. We use language to capture our understanding of the world around us, to communicate high-level goals, intentions, and objectives, and to support coordination with others. In computer science, and actually in the study of AI, we use knowledge representation languages and programming languages to communicate with computers in an unambiguous way. Importantly, language can provide us with useful and purposeful abstractions that can help us to generalize and transfer knowledge to new situations. So we're using, and we're using all sorts of different languages. And what I want to talk about now is how we can use language to communicate with agents, and in particular, formal language. So I want to talk a little bit about the affordances of formal language. So when I say formal language, I think about it in broad terms. So I don't just mean, you can think of a programming language, but you can also think of, or a knowledge representation language, or a database language. But I also want you to think more broadly about other languages that we as humans have created. We've created all sorts of beautiful mathematical languages like calculus or algebra to study physics, to study how the world works and to communicate it with each other in a very concise and beautiful way. We've created language for music as well, to create annotations for music and to communicate music to other people in written form. So here are some of the affordances of formal languages. It usually has a well-defined semantic, so it's unambiguously computer interpretable, which is great. It has a compositional syntax and semantics, which you're going to see that we're going to exploit here to good purpose. Some languages are declarative, which means that you can write them down and you can switch around the order in which you've written them down and they still have the same interpretation. That's not true of natural language. If I say the sentences have to be in a particular order to make sense, but with a conjunction, for example, of logical formulae, you can rewrite them and the conjunction still has the same meaning. They're typically concise. So we say a lot with a little. And other things are we can infer through the semantics of the language. So even just think about a set of linear equations, x plus y equals 5, x minus y equals 3. You can write down a whole bunch of things, but implicit in that, if you solve it or use Gaussian elimination, is the value of x and the get value of y and the value of z. And similarly in logic, we can entail a lot of things from a very concise and parsimonious representation. So that's a really great thing about, and we use this in language too to say, to imply things that are not explicitly said. So generally there's a proof system, some sort of way of manipulating that formal language in order to extract what's implicit, and it often supports generalization as a consequence. So I also want to say that it's a gateway to establish theories. So when we think about large language models, or we think about, even in the context of what I'm talking about today, we think about different languages and the affordances of those languages. We can reason with those theories like physics, stoichiometry and chemistry, music. We can use formal methods to verify and to automatically synthesize things. And we can also, in AI knowledge representation and reasoning, we have all sorts of formal languages for default and common sense reasoning, for deontics, what we should do or what we are obliged to do, and probabilistic relational models. The story goes on and on. For the rest of this talk, I want to sort of return to this notion of sequential decision making, and I want to do a thought experiment sort of grounded in a particular application. So imagine that someday, perhaps in the not too distant future, you buy a robot and you're going to bring it into your home. And like a person that you might hire to come into your home, even though that person or that robot has a set of skills, maybe it knows how to do the dishes, that would be great, or the laundry or various other things, you still need to tell it about the nuances of your own personal environment. Maybe, I don't know, there's a fiddly door, or the step is broken, or your kids need to go to bed, or they're not allowed to play on their computers until they've finished their homework, whatever it is. We all have our stuff that we need to communicate to our robots. And so the question is, how do we advise, instruct, and impart knowledge to our AI? And how does an AI exploit this knowledge to learn and to act? And that's what we're going to be exploring today. So again, we're going to do this in the context of reinforcement learning, as I described previously. But unfortunately, the way in reinforcement learning, the vehicle that we have for communicating our objectives to the robot is a reward function. And that reward function is typically a mapping from a state to a scalar, or a state action successor state, some little experience, to a scalar. And that's a pretty impoverished way of communicating with a robot. And yet that's what's typically done. And I don't know how many of you have worked in reinforcement learning, but usually what happens is that some poor graduate student has to write a big Python program to convey whatever it is that they want the robot to do. So there are a bunch of challenges to reinforcement learning. There's actually it's a little bit old now, there's a good paper that sort of outlines some of the challenges of using reinforcement learning in the real world. But one is indeed that the reward specification is really hard. If you want your robot to do something complicated, it's hard to specify it, given that reward function model. The second is sample efficiency. If you just imagine closing your eyes and knowing that you can go left and right without a map of this environment and try to get to the bathroom or somewhere else where you're going to get a reward, it's going to take you a lot of time of bumping into walls and other things before you find the pathway to where you're going to get a reward. So reinforcement learning is very sample efficient when we don't have a model of our transition system. And it's also, it's also partially observable. All of our experiences of the world are partially observable. And even though many of us deal in systems where we make this idealized view that the world is completely observable, it usually isn't. And so that's a fundamental challenge. So I wanted to just illustrate some of the things that I might like to, these are just things I made up, I might like to tell my robot. Run the dishwasher when it's full or when the dishes are needed for the next meal. Make sure the bath temperature is between 32 and 40 Celsius immediately before letting someone get into the bathtub. That could be good for an assistive robot, or for a robot that's looking after your children who have to go into the bathtub. Do not vacuum while someone in the house is sleeping. Always serve the person who has been waiting the longest. just good manners or good conventions or protocol. And if you're driving in Quebec, and I suspect all of you know this is a law. If you're driving in Quebec, never turn right on a red light because you will get a ticket if you get caught. So we can describe, some of these things are goals, some of them are preferences, some of them are norms, some of them are laws. We can express all sorts of things in language. And the interest is, how are we going to convey those to our robot? I have one more that I want to tell you. Whoops, just a sec. Whoops. So this is a procedural instruction. When assisting someone from a car to the sidewalk, I always think about this because we're in downtown Toronto and we're beside 5 major hospitals that are on University Avenue, for those of you who've been in Toronto. And people are like dropping people off to go to the hospital, and sometimes they stop on a busy street, and it always terrifies me. Like when you're assisting someone from a car to the sidewalk, always open the car door closest to the person, help the person to standing, move them beyond the car door, close that car door, and then walk them to the sidewalk. What's important about this is that it's temporally extended. If I do half of these things, for example, if I help the person to standing, I shouldn't get half of the reward because I will leave that person in a vulnerable circumstance in the middle of the road. And so I want to just say that I want you to notice that these things this reward-worthy behavior is temporally extended. And somehow I have to think about how to map that into a reward function that's a mapping from state to scalar, or state action successor state to scalar, to meet that sort of Markovian paradigm that we're in. The other thing I wanted to mention with respect to the previous slide, some of the things on the previous slide, where am I pointing, is that these can be conflicting, and they can be hard to satisfy altogether, and aspirational sometimes. So how do we communicate this to our reinforcement learning agent? And not surprisingly, for the purposes of this talk, I'm going to advocate for formal language. And in particular, I'm going to talk about linear temporal logic just very quickly. So linear temporal logic is a propositional modal logic. It's typically used in verification for talking about properties of traces. So property of the trace of a program, or the property of the trace of an execution of a piece of hardware, where you want to be able to verify that all of the traces have a particular property. Or I want to synthesize a program such that all executions of that program have a particular property. That's where it's used, and it's commonly used in verification. So what it comprises is, like a typical logic, there are a set of propositions, things that are true and false in the world. I'm holding this clicker, I'm talking to you here now, things that are true or false about the state. But then, and they can be combined together using typical logical connectives like and or and not. I'm standing here and I'm holding the clicker and I'm doing this, or something else. But they're also decorated with a set of temporal modal operators that allow you to talk not just about a particular state, but about patterns of the evolution of states. So there are modalities like next, until, eventually, and always that allow us to talk about complex patterns of sequences of trajectories. And that's very powerful because now we can talk about behaviors. We can talk about always making sure that the bathtub is a particular temperature immediately before letting somebody into the bathtub. Or we can talk about not vacuuming at the same time, always not vacuuming in every state. Don't vacuum if somebody is sleeping. And so we can use these logics to specify some of the things that I described before in a very easy way, and in what I believe is a very natural way. The other thing, the other thing that's good to know about LTL is that it's interpreted over finite or infinite traces, and that it can be transformed into an automaton, or multiple automata. And this is actually very important, so remember this. So here's just a very simple example. Do not vacuum while someone is sleeping. It's always typically written as a box. There are 2 propositions. Vacuum is true or false. Sleeping is true or false in a particular state. We don't want those things to co-occur, so we want to say always not those things co-occur in the state. So that means that at every state that is enforced. And that's what we would typically think of as a safety property. When we think about safety critical systems, there's certain states that we never want to be in this particular, for my robot in my house, this is one that I don't want the robot to ever create. So how do we communicate this to a reinforcement learning agent? Now we're back to that function, that R of S or R of SAS prime. And the answer for the purposes of this talk, we've done things with linear temporal logic directly, but for the purposes of this talk, I'm going to talk about automata. And remember, by linear temporal logic, things that I told you about can be mapped to automata. So just a little aside, just to speak to the richness of this, of what I'm doing. How many people have heard of Noam Chomsky? So that's the dude on the there on the right of your screen. He's known, you might know about him because he's a linguist, but you might also know about him. But he has quite strong political opinions that he likes to share with people. So, but here I'm interested in just mentioning very quickly Chomsky's hierarchy, which is a hierarchy of increasingly expressive languages, all the way up to from type 3 all the way up to type 0. Which is equivalent to Turing machines. So it's a model of computation as well as a model of languages. And the important thing that I wanted to point out is that any type 3 regular language, so that's a language that has clean iteration and concatenation, cleany star, can be compiled or transformed into a finite state automaton. And that means that I'm going to tell you we're going to use automata to represent our reward functions, and the important thing to take here is that any regular language can be compiled into these automata. As you go up, context-free languages can be mapped into pushdown automata, which requires some sort of external memory, and so on, all the way up. So some of the affordances of automata, it has a normal form representation. So all those different languages can now all be represented as an automaton. It exposes a function structure, allowing for compositional learning and transfer. It distinguishes context. It's really a Markovian decomposition, as we'll see in a minute. And it's a pathway to understanding computation. As we'll also see, it supports counterfactual reasoning. And we can define sub-languages. So a good way to think about an automaton is also that it is a recognizer or a generator of languages. So once you have this reward-worthy behavior in an automaton, which is what I'm going to advocate for, you can think of that not only as a recognizer, something that's going to tell you what reward you get, but you can also generate traces that have reward-worthy behavior. So my claim is that the alphabet and compositional syntax and semantics of formal languages can help reinforcement learning agents learn what to remember, and plan. So, and for the rest of the talk, this is what I'm going to talk about. I'm going to talk about reward machines and then some of the ways that we learn with it. And reward machines was the topic of Rodrigo Torrecarta's thesis. So here's a very simple example. I've got a grid world environment. I've got a little purple agent, and the agent is going to go to, in an office world environment, I'm going to go to A, to B, to C, to D. That's the task that I want the robot the agent to interact with, or to execute. And every time it does one loop, I'm going to give it some reward, but only when it does one loop. So this environment has sorry, let me do this. Oh, there we go. So a simple way to do this is that I could write a simple program, and that program requires a counter to keep track of what it's doing. But I could write this as a program, and that might be the way that you would typically do it. It's not a very hard program. You just need to keep track that it's gone to A, then B, then C, and then when it gets to D, it gets a reward of 1. But what we're going to do instead is we're going to represent it as an automaton. So we're going to translate that type 3 regular language into an automaton that I will call a reward machine. And we're going to encode the reward function in a vocabulary, a set of propositions. We've got coffee, you're at coffee, true or false. You're at the mailroom, true or false. You're at the office, true or false. Those little stars are furniture or some sort of other obstacle that you don't want to hit. Or you're at A, B, C, or D, and that's either true or false. So a reward machine is like a Mealy machine, for those of you who are familiar with that, but it's comprised of a finite set of states, U, here, U0, U1, U2, U3, an initial state, U0, which is where it starts, and a set of transitions that are labeled by 2 things. They've got a logical condition. Here the logical conditions are just, not A is true, I stay here. As soon as A is true, I transition to U1. So a logical condition, and then, or a guard. And then also here a function. This is actually a zero-ary function. It's actually a scalar. I'm going to give a reward of 0. But I could actually, in a more complicated setting, call a function that will actually compute something more sophisticated. So this is a very simple example, just so that you get the idea of how the reward machine works. And just to show you, so I've got this little robot here, this little agent, and I'm going to move up to A. So when I'm initially in U0, and when I move up to A, I'm going to communicate that to my reward function, which is now represented as this automaton, and it'll transition within the automaton to U1, and it will return a reward of 0, because I don't get any reward until I've gone all the way through the cycle. But that's how this reward function that is now represented, this non-Markovian or temporally extended reward function, that is represented in terms of this automaton. And again, we've now captured something that relies on the history, but you can think of it as a Markovian decomposition of this temporally extended reward function, where the state of the reward machine is actually a proxy for stuff that I've done in the past that will allow me to eventually get to the point where, when I get a non-zero reward, I have actually done it properly. So hopefully I've convinced you that of that. I just want to say there are many of the expressiveness of the language, but just to give you a sense of some of the flexibility. Deliver coffee to the office while avoiding furniture. So once coffee and not furniture is true, I transition here. And then once I've gone to the office, I transition to U3 and I get a value of 1. Or if I hit any furniture, I'm in a sync state that I can never return from. Similarly, deliver coffee and mail to the office. I can either deliver coffee and then mail and go to the office, or I can deliver mail and then coffee and go to the office. So we can have partial order representations as well. So again, that addresses the expressive power. We've now got something that can represent the expressive power of these temporally extended, very rich, complex reward functions that can be represented, written in any regular language, and then or linear temporal logic, interpreted over finite traces and represented as a reward machine. I want to now talk about how we're going to learn with that structure. So we developed a whole bunch of different algorithms that we tested out for using reward machines and for understanding how they work in the context of reinforcement learning. I'm going to tell you just about a couple. So, and there's a very simple insight that sort of is common to all of what we did, which is that we're going to give the agent access to the reward function. It's actually interesting. It's such a simple idea, and it's funny that it's not something that a lot of other people do. So the insight is that, you know, when you and I interact with the environment, and you eat ice cream plus 100 for eating ice cream, or if I bump into this table and stub my toe, I get a minus 20. We are wired for pleasure and pain immediately, but a robot is not. Or a computer program is not. Somebody always needs to program that reward function, or it needs to be learned somehow, but there is some code that tells the agent whether it is getting reward or not. There's some signal from some external source. So if we've written it as code, why not share it with the learning algorithm so that the learning algorithm can actually exploit that structure in learning? And that's exactly what we did to great gain. So we're going to, and then in addition to sharing it, I mean, you could just tell it what to do, but we're going to exploit the compositional structure of that reward function to learn much more quickly. So let's look at the first thing we tried, which actually turned out we ended up using as a baseline. So the observation that I want you to make is that a reward machine may define a non-Markovian reward function. So it doesn't just depend on the current state, but it depends upon the value that you get from the reward depends upon the history. And just to bring that home very quickly, very, very concretely, if my little robot came in and went to A, then it would have transitioned to U1, but then it went to this spot to the left of D immediately. It would be in U1 within the reward machine because it hadn't gone to B or C or D yet. And when it moves to D, it gets a reward of 0. However, if the robot had gone from A to B to C and it was still in the same spot that it was on the previous picture, but it had gone to A, B, or C, now it's actually in U3 of the reward machine. And so when it does the same action, moving from the left of D to D, it now gets a reward of 1. So same action, different reward, because we are looking at it from a Markovian perspective. From a Markovian perspective, it's getting different answers, and that's because it's relying on the state history. So these reward machines are capturing non-Markovian reward functions. So if you think about that, then the obvious thing to do is, well, why not just give the agent the state of the reward machine in addition to the state that it already has, and that should be sufficient to disentangle, when it gets the 1 and when it gets the 0. And that was the first thing we tried, and it didn't work very well, so I will show you that later on, but that becomes our baseline. What we did some work with hierarchical reinforcement learning. I can talk to you about it afterwards. I think we don't have time to go into it, but that turned out to be an interesting. We did hierarchical reinforcement learning just as a baseline. Hierarchical reinforcement learning, for those who don't know, is where you create sort of macro actions called options, little macro actions of skills, and then you assemble them together. You piece them together in order to do something. So we could have a skill that says go to A, and a skill that says go to B, and a skill that says go to C, and then you piece them all together using a meta controller. So we used hierarchical reinforcement learning. We used hierarchical reinforcement learning informed by the reward machine as well to give it the same sort of information. I can show that to you. And then the thing I want to elaborate on is an algorithm that we developed called Q-learning for reward machines, or QRM. And it's going to do all the things we did before, but it's also going to employ counterfactual reasoning. And this was the secret sauce that made this work really well. So again, we've got our reward machine, which is our reward function that captures this non-Markovian reward in it. Here's what we're going to do. We're going to learn one policy or Q-value function per state in the reward machine. So that Q-value function talks about the value of a state in an action. And we're going to have one for each state in the reward machine. We're going to select actions using the policy of the current reward machine state. So those policies that we're developing are going to tell us what to do. Okay? Yeah, there's a strong story. I'm not going into the details of how Q-learning works, but I think you can still learn this. We'll see the equation in a minute. And then what we're going to, so in U0, I'm going to use Q0, and U1, I'm going to do Q1, et cetera. And then the important thing that we're going to do is we're going to reuse the experience to update the Q values of all of the other states counterfactually. So even though I'm actually in U1 of the reward machine, I'm going to say, what if I performed this action and I got a state, action, and successor state, what reward would I have gotten if I'd been in U2? What reward would I have gotten if I was in U3? What reward would I have gotten if I was in U4? And by doing that counterfactual reasoning, I'm generating much more data for my actual experience in the world, and I'm getting more bang for my buck. I'm decomposing the construction of this overall policy that's going to tell me what to do by using the compositional syntax of the reward machine. So here's just a very simple example. We're going to select an action according to the reward machine state. We're going to update each Q value as if the reward machine is in the corresponding state. So for example, if I'm here, I'm in U1, I'm going to get a value of 0. And this is the Q function. This is the Q value function. So I'm going to update the Q0, Q value function. It's comprised of the immediate reward plus the discounted, this is a discount factor, future return. So, and future return from where I'm going to be after I perform that. So I'm still going to be in Q0. So it's going to, look into the future. This is a dynamic programming algorithm. So it looks backwards to figure out the future return. But I'm also going to say counterfactually, what else is going to happen? If I were instead in my brain in U1, then I would still have gotten this reward of 0, and I would get the discounted future return from Q1. Similarly for Q2, Q3 is a little different because what we see is that in Q3, if I'd gone to A, then B, then C, and I moved here, then I'm going to get a reward of 1 because I will have done the loop. And I'm also going to transition back to U0, so I'm going to get the future return from state Q0 again. So this is a very simple example, but you can imagine very complicated behaviors. We can write them in linear temporal logic. We can write them in in any regular, type 3 regular language, and we can represent them in an automaton with this, exploiting this type of structure and get huge sample efficiency gains. So for those of you who know a little bit about reinforcement learning, there's something called reward shaping, which is the way, one of the problems we have with reinforcement learning is that most states give no reward, and that means you're walking around without getting a signal. So one of the things that people do is something called reward shaping, which you can imagine is like taking the cookie, and rather than me having to find the cookie, that I could take the cookie and sprinkle a trail of how to get to the cookie, and that would give me a little bit of reward on my way to getting to the cookie. It's the same sort of thing, but it's done mathematically using a potential function that transforms the reward function, and we've done work on that using value iteration. And the nice thing about reward shaping is that for some of these algorithms, they will preserve the optimal solutions, and so they will preserve any optimality guarantees that you have from your algorithm. So we did some work there that I'll talk about more in a minute. And then the other thing that I just wanted to mention very, very briefly is counterfactual experiences for reward machines. So as you'll see in the experiments, we did this for tabular domains. I had a very simple tabular domain example here, but we also did it for deep learning domains as well. And when we originally did it, we wanted to keep on exploiting, the state of the art in deep learning algorithms, and it became tricky for us to always implement the different reward functions for each state of the automaton. And so what we ended up doing was doing something different for deep domains, which I'm going to tell you about in a minute. But just as a refresher, remember that QRM, which I told you about was this counterfactual algorithm, learns multiple Q functions, one Q function per state of the reward machine. And so instead, with CRM, what we did instead was that our Q function actually had an index to the state of the reward machine. So there's now one mega function, which is the cross product of the state and the state of the reward machine. And then we're similarly, conceptually, we're still synthesizing these counterfactual experiences for the reward machine states, but it's a tuple that is representing that state, not just one Q function for each one of the states of the reward machine. And that made it much easier to implement and sort of plug into new algorithms because it was just this one, tuple state. CRM behaves identically to QRM in tabular domains, and in deep domains it's a little bit different, but similar. So and again, the nice thing about what we've done with reward machines relative to hierarchical reinforcement learning, for anybody who knows it, is that hierarchical reinforcement learning does not provide any optimality guarantees because it's myopic in the way that it sort of pieces together the building blocks, those skills, in order to create an overall behavior. I'll show you an example in a minute, but that's the good thing to remember. Whereas there are algorithms that do give guarantees of optimality, and where we use those algorithms in learning, such as Q learning, we preserve those optimality guarantees with our algorithm using reward machines. And so just stated informally, QRM and CRM with reward shaping, or not with reward shaping, because reward shaping also preserves those guarantees, preserves optimality guarantees of Q learning and reward shaping. They converge to optimal policies where there is no function approximation. Of course, as soon as we're dealing with perception, if we're dealing with images or we're dealing with continuous domains, we immediately have function approximation, and so we, like everybody else, loses those optimality guarantees, but this was a really nice result. So let's look very quickly at how these behave, and I'm just going to blast through these. Some of this work, this is actually older work that we've done, and so some of these experiments are old, but I thought it was good introductory material to sort of open the gateway to a number of things that we've been doing, and we've done a lot of follow-on work. So here's the office world domain. You've seen this before. The important thing that will be repeated is that I've got these graphs. On the y-axis is the normalized discounted reward, which means that 1 is the perfect reward. And on the x-axis, I've got the number of training steps. So ideally what you want is no training steps and optimal reward. So I've got the two betters on here, and what's plotted are four different algorithms of the ones that we saw before. Q-learning over the cross product, which was the obvious thing that we thought to do but with no counterfactual reasoning, in blue. Hierarchical reinforcement learning in yellow. Hierarchical reinforcement learning with knowledge of the reward machine state to help the meta controller decide what to pick. And then our QRM algorithm. And what you'll see immediately is that our QRM algorithm is very sample efficient with very few samples relative to the others. It converges to the optimal solution. This is our baseline where we just gave it the reward machine state, but we didn't do counterfactual learning. And these are the two hierarchical reinforcement learning algorithms in the middle. And I'll talk, actually I think I've got it on the next slide. Yeah, so hugely sample efficient. Why does HRL not work well? I just want to, it's really simple once you realize it. So here, imagine that I have the task of getting coffee and then going to the office. So two things, and I've got an option for getting coffee, and I've got an option for going to the office. The meta controller is always going to choose the best myopic thing to do. So the first thing it has to do is go and get coffee. So it's going to go to the closest coffee place, which is 10 steps away. Oh, sorry. So this is the optimal solution. The optimal solution is to go to the 10 steps to the coffee and then go to the office for a total of 13 steps. That's the optimal solution. But what the hierarchical reinforcement learning, or the system, which is myopic, is going to do, it's not going to look ahead and think it has to go to the office after it goes to the coffee station. So it's going to go to the closest coffee station, which is only 7 steps away rather than 10. But in doing so, then it's committed. And then it's going to take it a huge number of steps to go, all 18 steps to get all the way to the office. So that's why hierarchical reinforcement learning is suboptimal. Sometimes, optimality is sometimes overrated. Hierarchical reinforcement learning is great, and a lot of times we don't care about optimality. So I like hierarchical reinforcement learning a lot. We've used it as well, but I just want to point out that distinction. So craft world domain, same example, another a little bit more complicated domain that is a grid world domain. Again, we have the same y-axis and x-axis, but what I want to point out, and the same color coding, I want to point out that after 10 to the 6 training steps, we're still getting no signal from this Q-learning algorithm that is not using counterfactual reasoning. And the important thing to know about this is this algorithm is guaranteed to converge to the optimal policy, which means that at some point in the future it's going to get up to 1. But that future is a long way off, and I think it's really evocative of this sample efficiency problem and how important these algorithms are to really help you to get optimal solutions. It's really striking. It's really, really striking. So we had similar results. This is it's called a water world domain. It's like playing billiards or pool. You're controlling the little white ball, and these other balls get hit and they move all over the place. So it has some function approximation. Again, so this was some deep learning results were in red, so we did a lot better, of course, than the 2 hierarchical reinforcement learning systems and the baseline where we're not doing counterfactual learning. And then the last example I wanted to give you, this is a different, I grabbed this from a different paper. This is the CRM algorithm that we used, which is the one where we have the tuple. This is another deep learning domain. Some of you who do reinforcement learning may recognize this half cheetah. And we were doing reinforcement learning here, and the color is a little bit different, but this is our CRM algorithm. This is hierarchical reinforcement learning with the reward machines, and then these are the other two. And again, you see the baseline at the bottom where we're still getting no signal with what were then state-of-the-art techniques. This was with reward shaping, CRM with reward shaping. Interesting, and this is sort of interesting, I wanted to show you again. Task 1 required you to look ahead in order to get optimal solutions. The cheetah was going back and forth, and so it needed to know that it was going to have to slow down when it got to the wall so that it could turn around and go back, and it needed to know that it needed to know what was coming in front of it. Whereas the second task was just like go to one station, then the next, then this next. So choosing the locally optimal solution actually was fine and would lead to global optimality for task 2. And in that case, I wanted to point out that hierarchical reinforcement learning worked better. I'm not quite sure how, we're not quite sure why, but just to say that's, that was something we left for future work to figure that out. So the final thing I wanted to talk to you about, hopefully I've convinced you that reward machines are a really expressive way of representing rich, temporally extended, complex, reward-worthy behavior, which I would argue is typical of what we want to do, and it has some of these great properties when combined with these algorithms that allow it to exploit the structure and function of these reward functions. But the question is, where do these things come from? Maybe we all feel very comfortable writing automata, but not everybody does. And your grandmother who may have a robot in her house is not going to write a reward machine for us. So I just wanted to observe that we can specify them, we can generate them, and we can learn them. And just very quickly, again, the nice thing about this normal form representation is that one size does not fit all. I can write some things in linear temporal logic, some safety constraints. I can write a little programming, some other behavior in a little type 3 programming language, and they can all be combined into a reward machine structure. So I can write in any language, and we actually developed some things where we combine these things and using into a DFA, into a deterministic finite state automaton, and then compiled it into a reward machine. And we've done work, there's a lot of work now for those of you who may follow the work in language models or other cases on in translating natural language to formalizing natural language, and we've done some work in formalizing reward machines, as have other people who have been really interested in reward machines. And again, once you've got that normal form representation, you can use QRM, CRM, reward shaping, or any other algorithm that anybody else may come up with, because you've now got this normal form representation. So if you want to write in Python, you don't have to write a Python-specific language, or you don't have to write something that manipulates a particular language, because we've got this normal form representation. The other thing we can do is generate these reward machines. We can generate them from high-level planners using PDDL planners. We can generate them from LLMs or other ways. And we did a little bit of work, just as one thing, where we used a high-level model to describe an abstract action as options and used a PDDL planner to generate a plan. And we used a deordering algorithm by somebody that we know, Christian Muse, to then deorder that sequential plan so that we got all the different orderings. So now our plan was not just one linearization, but an embodiment of many, many linearizations. And then we used, so that we had the high-level instructions for how you would pick up something and go over and get a cookie, those high-level instructions, but not how much pressure I have to put on this clicker in order to actually pick it up. Those are things that you want to learn from trial and error, because you pick up things very differently. So that sort of trial and error was sort of subcontracted to the reinforcement learning algorithm, whereas for the high-level strategy, we used a symbolic planner. And that turned out to be really, really great thing to do. And yeah, so the last thing I wanted to talk about very quickly, and then I'm going to be done, is that we can also learn these. So we were originally interested in learning reward machines to learn what to remember in partially observable environments. And I'm going to tell you how we did this. But since then, there are a lot of people who have been really interested in reward machines, a lot of people, particularly in robotics, who have adopted reward machines or explored reward machines for some of their work. And so a lot of people have done work in learning reward machines. And I can point you, we did a big sort of summary of the state of the art when we wrote a journal paper that I can tell you a little bit about. But this is sort of a cute, evocative example that I just wanted to tell you, just to show you why you might want to learn how a reward machine can help you in a partially observable environment. So imagine you've got this agent, and it's connected with via corridors with 3 different rooms. The yellow room has a button in it, and when that button is pressed, a cookie magically appears in one or the other of the blue or the red rooms. And the agent gets reward from eating cookies. So it's maximal expected cumulative reward. The more cookies it eats, the more reward it's going to get. But the problem is that this environment is partially observable. So the agent only sees what's in the room that it's in. So it only sees that it's in a corridor, and it can only see the button once it's in the yellow room, and most importantly, it can't see where the cookie is, or even if there is a cookie. And it doesn't know that, again, we're in this paradigm where we don't know what the actions do. So it doesn't know that when it presses the button, it's going to get a cookie. It doesn't know that when it goes into the room where the cookie is, that it's going to be able to eat that cookie. And those are all things it has to learn. All it knows is that it's going to get a reward if it eats a cookie. Well, all it discovers is that if it eats a cookie, it gets a reward. So it's a partially observable environment. It doesn't know what's in these. And what it does is that over time, it actually has these experiences and learns a reward machine. It learns so that if it starts in the beginning and it should go to the yellow room first, and then if it goes to red room and there's a cookie, then it gets a 0. And so on and so forth. And if it actually eats that cookie, which is what the white cookie means, then it gets a reward of 1, and so on. So it learns what to remember about the past, so that when it's here, it needs to know. So the problem is that when it's here, it doesn't know what to do. At the beginning, it needs to learn to go and press the button, which is what that says, because then a cookie will appear. But then it's back down here, and it still doesn't know what to do. If it goes here and it eats the cookie, then when it comes back here, then it needs to go up again. But if it goes here and then goes here and it hasn't eaten a cookie, then it needs to go here, and so on and so forth. So the problem is knowing what to do when you get here, and that depends on what's happened in the past. And so the structure of the reward machine does that. And we actually we tried a whole bunch of different techniques for learning those reward machines, and it turned out that local search worked the best of all, but we represented it as an optimization problem. And it's sort of fun just to look at the construction of the optimization problem. So again, when we learned with reward machines, we got great. When we learned a reward machine and we used it in these deep environments, we did very well. When we didn't, we flatlined. So really hard even a simple problem like that was really hard to learn because you just don't get enough signal. So just to recap, I'm done. The question that I asked was, how do we advise, instruct, task, and impart knowledge to an AI that learns? I talked about the challenges of reinforcement learning, reward specification, sample efficiency, and partial observability as just some of the myriad of challenges that we have to address. The claim that I made was that the alphabet, compositional syntax, and semantics of language, here formal language, but I think that the claim is true more generally, can help RL agents learn what to remember, and reason. And that formal language, but language more generally, is a powerful and effective tool to advise, instruct, task, and impart knowledge to an AI. So hopefully I've convinced you of that. The big idea was that we were going to write our functions, our reward functions, our temporally extended, rich, complex reward functions in a normal form representation of a reward machine. We were going to reveal the reward function, that reward machine, to the agent so that it could use it in learning. And the other key insight was that where did those reward machines come from? We can specify them, we can generate them, or we can learn them from data. And the takeaway is that the alphabet, compositional syntax, and semantics of formal languages can help reinforcement learning agents learn what to remember, plan, and reason, and that formal languages really are powerful and effective tools to help us in achieving that objective. Since we've done that work, we've done a lot more work. We've done work on noisy reward functions. We've got these propositions, but where do those propositions come from if you're dealing with a vision or a haptic or other sort of model? So we have to write labeling functions, which are abstractions, and those labeling functions can be noisy. So we did noisy reward machines. We did some work where we were learning those labeling functions, those abstractions to the propositional state from online with data in a particular environment. We also moved up the Chomsky hierarchy and looked at push-down reward machines and some algorithms related to push-down reward machines. And we've also done quite a bit of work on end-to-end systems where we use linear temporal logic natively together with something called a progression function that sort of eats away at what you've already satisfied and keeps track of what you haven't satisfied yet, in order to do reinforcement learning. And lots of other work by us, but also a lot of work by other people who have adopted reward machines and found it interesting. So again, I want to give acknowledgments to Rodrigo Torrecarta for the reward machines work. This was his PhD thesis work in collaboration with Torin Clausen and Rick Villanzano, and Alberto Camacho, who did some related work, and actually some prior work in advance of Rodrigo's work. And then everybody else here who has contributed either directly or indirectly to some of the follow-on work. There's code, there are papers to read. I'll just put these up because they'll be part of, I guess, the record. More recent work that we've done. You know, this LTL to actions really is nice because it's learning the language of LTL in a way as in order to really be able to operate. And again, there's been a lot of follow-on work to that work as well, and other related work. We also, years ago, for those of you who may be interested in symbolic planning, we did a lot of work with PDDL planners and planning with linear temporal logic. And so there's a lot of nice old work that's been done that I think is just really still has currency. So thank you very much for your patience, and I'm happy to take questions. So thanks.